Everyone. Welcome to SWAM's online lecture series on the topic Database Management System. I am Muhammad Ubaidullah Bukhari, working as a professor in the Department of Computer Science, Aligarh Muslim University. Today, we are going into some key concepts that will unlock the secrets of database design, lossless join, dependency preserving decomposition, along with the including closure property. Get ready to simplify complex ideas and supercharge your database skill with us. In the previous session, we have discussed the following: functional dependencies, multi-value dependencies, and join dependencies. Before proceeding with the today's agenda, I would like to discuss some questions that I had given you in the last class. What are the functional dependencies in database? The answer is functional dependencies in database define relationship between attributes in the relation. They express that a given set of values in one set of attributes, there is a unique set of values in another set of attributes. In simpler form, functional dependencies predict how the value in a certain column determine the value in other column within a table. For instance, a table of employee, the social security number might functionally determine the employee's name, implying that each social security number is associated with only one name, forming a functional dependency. The next question was, why are functional dependencies important to database design? The answer is, functional dependencies play a crucial role in ensuring data integrity and optimizing data design. By defining the relationship between attributes, functional dependencies help minimize the data redundancy and anomalies like insertion, updation, and deletion anomalies. They aid in normalization, breaking down complex tables into a smaller, well-structured one, enhancing data organization and reducing redundancy. Functional dependencies also facilitate query optimization by enabling the query optimizer to make informed decision about indexing and query execution strategies. Overall, understanding and enforcing functional dependencies promote efficient, scalable, and maintainable database systems, enhancing data reliability and query performance. The third question was, what do you mean by multi-value dependencies, and explain in details? The answer is, multi-value dependencies in database extend the concept of functional dependencies by specifying dependencies between the set of attributes rather than individual attributes. They occur when there are multiple independent relationships between attributes in a table. Formally, a multi-value dependency exists when for every combination of values in one set of attributes, there are multiple corresponding combination of values in another set of attributes. MVDA multi-value dependencies are crucial for ensuring data integrity and normalization in database design, particularly in scenarios where attributes exhibit a complex interdependencies beyond the scope of traditional functional dependencies, thus requiring careful consideration during schema design and normalization processes. The last question was, explain join dependencies in detail. The answer is, join dependencies in database describe the rules for combining tuples from different tables after a join operation. They ensure that certain relationships hold true among the resulting tuples. For example, if we have a table for employees, department, and projects, a join dependency might specify that for every combination of employee, department, and project, there must be a corresponding tuple including the employee's assignment to the project within their department. Joint dependencies help maintain data consistency and integrity in the relational databases. So let's start the agenda of the 2 days lecture. As today we will going to discuss closure property, next will be relational decomposition and dependency preserving composition. Dependency preserving decomposition. Closure property. In database management system, the closure property refers to the ability of a set of functional dependencies to imply additional functional dependencies. In simpler terms, if you have a set of attributes in a relation, or you can say table, and you know certain functional dependencies, that is relationship between attributes, closure property allows you to deduce further dependencies that actually follow from the given ones. For example, let us say you have a relation with attributes A, B, and C, and you know that A determines B and B determines C. With the closure property, you can deduce that A also determines C because of transitive property. Relationships between A, B, and C. The closure of a set of functional dependencies is a set of all functional dependencies that can be logically derived from the given set. This is important in database design, optimization, particularly in normalizing a database to minimize redundancy and ensure data integrity. Steps in computing the closures. To compute the closure of a set of functional dependencies, you typically follow these steps. The first step, start with the given set of functional dependencies. Let's denote the given set of functional dependencies as F. This set consists of functional dependencies from the form X determines Y, where X and Y are a set of attributes. Second step, apply Armstrong's axioms. Armstrong axioms are a set of inference rules used to derive new functional dependencies from a given set. These axioms include reflexivity, augmentation, and transitivity. Reflexivity. If Y is a subset of X, then X determines Y. Augmentation. If X determines Y, then XZ determines YZ for any attributes of a set Z. Transitivity. If X determines Y and Y determines Z, then we can say that X determines Z. Third step, apply the reflexivity property. Apply the reflexivity rules. For each attribute set X, include X, X determine X in the closure. Step 4. Apply the augmentation rule. For each functional dependencies, X determine Y in the closure if there exists a set of attributes Z such that XZ determines YZ is not already in the closure. Add it. Step 5. Apply the transitivity rule. For each pair of functional dependencies, X determines Y and Y determines Z in the closure. If X determines Z is not already in the closure, add it. Step 6. Repeat the steps 2 to 5 until no new dependencies can be derived. Continuing applying Armstrong's axioms iteratively until the closure no longer changes. This ensures that you have derived all possible functional dependencies from a given set. These steps provide a systematic approach to computing the closure of a set of functional dependencies in database management system, which is essential for database design, normalization, and maintaining data integrity. Armstrong rules for closure property. Armstrong's axioms are a set of rules used to derive additional functional dependencies from a given set of functional dependencies. These axioms provide a systematic approach to computing the closure of a set of functional dependencies in a relational database. Let's understand each axiom in detail. Flexibility axioms. Flexibility states that if y is a subset of x, then x determines y. In other words, if you have a set of attributes x, then you can always infer that x functionally determines itself. Mathematically, if x is a subset of y, then x determines y. For example, if you have a functional dependencies A determines B, you can apply the reflexibility axiom to deduce that A determines A, B determines B, and so on. Augmentation axiom. Augmentation states that if x determines y and xz determines yz for any attribute z, this axiom allows you to add the same attributes to both sides of a functional dependency. Mathematically, if x determines y, then we can say that x determines yz. Transitivity axiom. Transitivity states that if x determines y and y determines z, then x determines z. This axiom allows you to chain together multiple functional dependencies to infer new one. Mathematically, if x determines y and y determines z, then we can say that x determines z. For example, if you have a functional dependencies A determines B and B determines C, you can apply the transitivity property to deduce that A determines C. Armstrong's axiom provides a systematic method for computing the closure of a set of functional dependencies, which is essential for database design, normalization, and ensuring data integrity in relational databases. For example, the following set of functional dependencies F is equal to F determines B, B determines C. Answer. The closure of these functional dependencies are: first, reflexivity. We start with adding reflexive dependencies. A determines A, B determines B, C determines C. Second, augmentation. We apply the augmentation rule to derive additional dependencies. A determines BC. Transitivity property. Finally, we apply the transitivity rules to derive more dependencies. A determines C. So the closure of a given set of functional dependencies is A determines B, A determines C, B determines C, and A determines BC. The next topic is relational decomposition. Relational decomposition is a process in database management system where a single large relation or table is broken into smaller, more manageable relations. The main objective of relational decomposition is to minimize data redundancy and dependency while preserving the original data's meaning and relationships. This is typically achieved through techniques such as normalization, which involves organizing data to eliminate redundant information and ensure that each piece of data is stored in only one place. During relational decomposition, it is crucial to consider factors such as functional dependencies between attributes, ensuring that the resulting smaller relationship maintain these dependencies. Lossless joint decomposition is also important as it guarantees that the original relation can be reconstructed from the decomposed relation without losing any information. Types of decomposition. Decomposition in database management system is a fundamental process in database design, aiming to improve the data organization, reduce redundancy, and ensure data integrity. The main types of decompositions are lossy decomposition and lossless decomposition. There are two types of decomposition, lossy or lossless. Now let's discuss first what is lossy decomposition. Lossy decomposition in database management system involves breaking down a relation into smaller relations in a manner that results in the loss of certain information or dependencies present in the original relation. Unlike lossless decomposition, which ensure that all the data can be reconstructed from the decomposed relation, lossy decomposition sacrifices some aspect of data to achieve other objectives such as improve performance or reduce storage requirement. This approach is often utilized in scenarios where preserving all details of the data is not critical, such as data warehousing or data aggregation task. For example, in a sales database, transaction level details may be aggregated to monthly sale total by product category, resulting in the loss of granularity, while lossy decomposition can offer benefit in terms of efficiency. Next is lossless decomposition. Lossless decomposition in database management system refers to the process of breaking down a relation into smaller relations without losing any information present in the original relation. The objective of lossless decomposition is to ensure that all the data in the original relation can be reconstructed from the decomposed relations without any loss of information. This is achieved by carefully identifying the dependencies between the attributes and decomposing the relation in a way that preserves these dependencies. Lossless decomposition is basically a crucial aspect of database normalization. Lossless decomposition is basically a crucial aspect of database normalization as it helps eliminate data redundancy while maintaining data integrity. While ensuring that no information is lost during the decomposition process, lossless decomposition enables efficient data storage, retrieval, and manipulation within the database. It plays a vital role in optimizing database performance and maintaining consistency across different database operations. Overall, lossless decomposition is a fundamental concept in database design essential for building robust and reliable database systems. Types of relational decomposition techniques. In database management system, there are several types of relational decomposition techniques used to break down a single relation. In database management system, there is several types of relational decomposition techniques used to break down a single relation or table into smaller relations. Each type aims to achieve specific goals related to reducing data redundancy, preserving functional dependencies, and optimizing database design. Here are some common types of relational decomposition. First is lossless joint decomposition, dependency preserving decomposition, basic or normal form decomposition, third normal form decomposition, Fourth norm for decomposition, lossless join decomposition. In database management system, a lossless join is a crucial category ensuring that when combining data from two relations, or we can say tables, through a common attributes, no information is lost in the process. This property is fundamental for maintaining data integrity and consistency in relational databases. Lossless join are achieved when the common attributes used for joining a key or a part of key in at least one of the participating relations. This ensures that each tuple in the resulting joined relation can be uniquely identified and reconstructed from the original relations. The primary goal is to maintain lossless decomposition is achieved when the original tables can be reconstructed through the use of natural join on the smaller tables. Lossless joins are essential for various database operations, including query processing, data integration, and schema design. They play a significant role in normalization process, where relations are decomposed to eliminate redundancy and dependency while preserving the ability to reconstruct the original data through lossless join. Importance of lossless join decomposition. Lossless decomposition is a paramount important as it ensures the preservation of the data integrity and consistency during the normalization process. By decomposing large relations into a smaller one without losing any information, lossless decomposition support efficient query processing, schema optimization, and data maintenance. Lossless decomposition is a fundamental concept in database system design that ensure that data integrity while minimizing redundancy and dependency. Here is a detailed exploration of its importance. Data preservation. Lossless decomposition guarantees that no information is lost during the process, enabling the reconstruction of the original table. This property is crucial for maintaining the data integrity and consistency throughout the database. Data consistency. It helps maintain data consistency by preventing anomalies and contradictions that may occur with improper decomposition. Lossless decomposition helps maintain the data consistency by preventing anomalies that may arise from redundant or inconsistent data storage. Minimizing redundancy. By organizing data efficiently, it reduces the data redundancy, which can save storage space and improve query performance. Query optimization. A smaller, well-designed table resulting from lossless decomposition can lead to faster query execution time. Lossless decomposition contributes to efficient query processing by reducing the need for complex and costly join operation. Scalability and flexibility. It supports the scalability of a database, making it easier to add or modify tables without compromising data integrity. Lossless decomposition support the scalability and flexibility of database system by allowing them to evolve over time without sacrificing data integrity. Normalization. Lossless decomposition is closely related to the process of normalization, which involves organizing database tables to reduce redundancy and dependency. By decomposing relations into a smaller one while preserving the ability to reconstruct the original data through lossless join, normalization ensures that the resulting schema adheres to higher normal form such as third normal form or basic odd normal form. The next is schema design and maintenance. Lossless decomposition guides effective schema design by providing guidelines for structuring relations in a way that optimizes data storage and retrieval while preserving data integrity. Transaction management. In transactional management, in transactional databases, lossless decomposition play a critical role in ensuring the atomicity, consistency, isolation, and durability. This is called acid property of a transactions. By preserving these integrity through lossless join, transactions can be executed reliably without compromising the database consistency or reliability. Benefits of lossless join decomposition. Lossless join decomposition in database management system ensure data integrity and efficient query processing by splitting relational schemas into a smaller, manageable one without losing information. This guarantees accurate query results and simplified database design, maintenance, optimization. It supports data normalization, reduces redundancy, and enhances overall database efficiency and reliability through improved data consistency and logical organization. Data integrity. It ensures that no information is lost during that tables. Data consistency. Prevent anomalies and contradictions that may arise with improper decomposition, maintaining data consistency. Query flexibility. Enables efficient querying by breaking tables into manageable pieces without sacrificing data accuracy. Reduce redundancy. Minimizes data redundancy, saving storage space and improving data efficiency. Simplifies updates. Eases the process of adding, modifying, or deleting data without compromising data integrity. The real-life applications, lossless join. Lossless join decomposition plays a crucial role in various real-life applications across different industries where data integrity, consistency, and efficiency are paramount. Here are some examples. Inventory management. Ensure accurate tracking of inventory level, preventing data discrepancies in retail and supply chain system. Supply chain databases track inventory levels, orders, shipments, and supply information. Customer relationship management maintains a consistency in customer data across where various touch points for effective marketing and support. Financial systems ensures precise accounting records, minimizing error in financial transactions and reporting. Banks and financial institutes rely heavily on databases to manage customer accounts, transaction, loans, and investment. Healthcare record preserves data integrity in electronic health records critical for patient care and medical research. Healthcare databases manage patient records, medical histories, test results, and treatment plans that when dealing with complex relationships between products, order, and customer, queries can be executed efficiently without losing any critical information. Telecommunication. Telecommunication companies handle vast amount of data related to customer accounts, network infrastructure, call records, and billing information. In all these real-life applications, lossless joint decomposition in database management system provides a foundation for robust, efficient, and reliable data management systems, enabling organization to make informed decisions, enhance operational efficiency, and deliver better products and services to their customer. Dependency preserving decomposition. Dependency preserving decomposition is a fundamental concept in database management system that ensures the integrity and consistency of data when breaking down into relation schema into a smaller schema. Let's delve deeper into the significance and some techniques involved: maintaining data integrity, avoiding anomalies, normalization, projection decomposition, and the last is dependency analysis. Third normal form decomposition. Third normal form decomposition is a technique used in database management system to break down a relation or table into a smaller relations while ensuring that each resulting relation in third normal form 3NF is a normal form that helps eliminate the certain types of anomalies related to transitive dependencies. To understand 3NF decomposition, let's first define the third normal form. In a relation is in 3NF if it is second NF and it has no transitive dependencies. Here's how the 3NF decomposition process typically works. The first step is to identify all non-trivial functional dependencies in the original relation. If any non-trivial functional dependencies violates in 3NF, that is, it represent a transitive dependencies, creates a new relation containing the dependent attributes and its determinant. Remove the dependent attributes from the original relation and add it to the newly created relation. Repeat this process until all resulting relations satisfy. Next is Boolean code normal form decomposition. Boolean code normal form decomposition is a technique used in database management system to break down a relation or table into a smaller or more manageable relations while ensuring that each resulting relation in BCNF. BCNF is a higher normal form than third normal form and is designed to eliminate the certain type of anomalies related to functional dependencies. To understand the BCNF decomposition, let's first define BCNF. A relation is in BCNF if for every non-trivial decomposition, for every non-trivial functional dependencies, that is X determines Y in the relation. X is a super key or Y is a prime attributes and attributes that is a part of some candidate key. Here, how the benefit. Fourth normal form decomposition. Fourth normal form decomposition is the technique used in database management system to break down a relation or table into a smaller relations while ensuring that each resulting relation is in fourth normal form. Fourth normal form is a normal form that helps eliminate certain types of anomalies related to multi-valued dependencies. To understand 4NF decomposition, let's first define the fourth normal form. A relation is in four-number form if it satisfies the following condition. First condition is it is in Boolean code number form and it has no trivial multi-value dependencies. Multi-value dependencies occurs when a set of attributes determines multiple independent set of values for another set of attributes. Four-normal form decomposition aims to remove these multi-valued dependencies by breaking down the relations into a smaller or more normalized relations. Here, let me tell you how the functional let me tell you how the four-normal form decomposition process typically works. First step is to identify all non-trivial multi-valued dependencies in the original relation. If any non-trivial multi-valued dependency violates 4NF, create a new relation containing the attributes involved in the multi-valued dependencies. Remove the attributes involved in the multi-valued dependency from the original relation and add them to newly created relation. Repeat this process till all resulting relations satisfy 4NF. Inclusion dependency. In database management system, inclusion dependency ensure that consistency by satisfying relationships between attributes across tables. It mandates that if data appears in one table, it must appear in another. Multi-value dependency and joint dependency can be used to guide database design, although they both are less common than functional dependencies. Inclusion dependencies are quite common. They typically show little influence on the designing of database. For example, in a scenario where one table lists employee and their department, IND ensure that every department mentioned must exist in other table. This maintains accuracy and reliability, contributing to the database integrity. The inclusion dependency is a statement in which some column of relations are contained in other column. In today's lecture, we discuss about the normalization of closure properties of database management system, lossless join, and dependency preserving decomposition. Now, let's assess your knowledge and track your progress with some important questions. Your answer will enhance your concept as well as make you more aware about the topic. The today's question to test your knowledge are: first is, what is lossless join decomposition and why is it important in database design? Next question, explain the concept of dependency preserving in lossless join decomposition. Discuss the difference between lossless join decomposition and dependency preserving decomposition. And the last question, explore the impact of lossless join decomposition on the performance of database operations such as insertion, deletion, and updating records. From exploring lossless join and dependency preserving decomposition to understand the closure property, we have strengthened our foundation in the database design and management. Let's keep this momentum going as we apply these principles to real-world scenarios and continue our quest for data mastery and continue our quest for database mastery. Remember to review the material and reach out with any questions. Until next time, happy learning. Thank you.